welcome to another episode of Undercooled. Today, it's just Tim and me. You're stuck with us.
For better or worse.
So we're going to talk about projects and the kinds of projects that we've done over the last few years. So I'm going to start by asking Tim to talk about what's one of your projects you're kind of proud of.
Yeah, I like to do projects instead of exams in most cases. And so as an end of semester project, there's always the question of what would be a good way to sum up the entire semester or the entire year even and say, how can students do something that they'll be proud of, that will be meaningful to them, that also lets them prove to me that they actually learned something? Because it is an assessment as well as something to do that has learning outcomes. And at the end of the lab year for our junior labs, we have a reverse engineering project. And so students will choose a commercial product that they're interested in for whatever intrinsic reason. It's a hobby, it's related to some family or friend that they have, something they always wanted to learn about but just never did. And so they choose the product, they propose the research plan, and they have a month to do a reverse engineering where they say, what is it made out of? How was it processed? Why was it made that way? What were design decisions that the product designers had to go through as they were working on this? And then we have a poster fair at the end of the year where they present on their reverse engineering work.
That's great. So can you give us some examples of some of the posters?
Oh yeah, so for this year even, they haven't presented yet. This is so fresh. Some of the projects include portable water filters. So the kind that you take hiking with you, that the sort of put it right in the stream and drink from it. And there's always this question of, are companies telling the truth? And it's an important question and one that's worth asking. So yeah, the water filters, we have climbing carabiners, we have a allegedly biodegradable phone case that is reinforced with allegedly flax fibers. So the students asked me yesterday, how would we get the elastic modulus of this? And I said, who's taking composites right now? And then the hand goes up. And I said, well, you know what you're on the hook for doing then. Right. What else? Historically, some great ones we've done. A lot of our students are very musical, so there's often a musical instrument related question, whether it's saxophone reeds or violin strings or guitar pickups. Those have all been topics in the past. Sports stuff, hockey sticks, skis, a motorcycle helmet one year. And yeah, it's just really all over the map because our students are interested in a lot of things. And it's good to be able to support that creativity, but also still really give them a challenging assignment that requires, and this is in the spirit of the assessment, to say, take all of the things you learned all year, bring them together, assemble them into a coherent whole, and show me that you can make sense out of not just one single experiment, but a whole set of techniques that have to be combined to answer an unknown question. What is this thing? I don't know. You don't know. The only way to find out is to actually do the work.
Yeah, I remember I've gone to some of your poster sessions and they're amazing. And I remember some people did things where they compared like a brand name product to a knockoff, something off Amazon, and talked about how the knockoffs are potentially dangerous because of the way they use batteries and the materials they use are real poor materials. So, they show that you get what you pay for, usually. Not always. That's great.
And sometimes they do get a result where, as you mentioned, they'll study two different products and say, I can't tell the difference between these things.
Yeah.
So then what's the difference? And the answer is not materials, it's marketing.
That's right.
And that can really affect prices quite a lot, it turns out.
That's great.
Yeah. But I've attended some of your classes as well where you've had your students give projects, and one that I've always been really impressed by the student work is the one where students have to build their own mechanical tester.
Yeah.
So tell me about that.
Well, first of all, I think I should make it clear, and I think you do the same thing. One of the things I do to make time for a project in a class that normally didn't have projects was to get rid of the exams. And if you think about how much time a student spends preparing for exams, it's a considerable amount of time. And then when you pair that with all the research that shows students don't remember anything, even a few hours after they take the exam, it makes you think, why am I giving an exam? Whereas a project, students are far more involved and they learn things in a way that you just don't learn studying for an exam. And yet if you structure it properly, you can still cover all the material that you wanted to cover on the exam and make sure that they have this practical understanding of the concepts that we teach
Right.
in class. So, I've taught our Introduction to Material Science class, which is traditionally taught as 3 50-minute lectures a week and then a recitation section with a graduate student instructor. And so what I've done is I've gotten rid of all my lectures. I have them read the book before they come to class. I have them organized into teams, and then I give them activities all through the day. And I use the whiteboard a lot. I've talked about this in other videos, but it's really like a giant recitation. But then we have our projects. And when I was covering, I sort of break the class up into 3 sections. I don't follow Callister exactly because I think, I start with the beginning of Callister, bonding. That's a great place to start. Then we do structure, and then we do, defects, and then diffusion. But then I cover very quickly energetics and kinetics. So I do phase diagrams and then phase transformations, whereas he puts in mechanical properties earlier. I wait until I'm done TTT diagrams. I say a little bit about properties, but I don't really get into it till the second middle part of the course. And that's where we do all of our mechanical properties and the different kinds of materials, metals, ceramics, polymers, and that's the middle part. And then the last part of the course is electrochemistry, composites, and electronic properties of materials. So for that middle part, I wanted to find a project that would speak to their understanding of different kinds of materials and the mechanical properties of those materials. Now, I had been talking quite a bit to my friend Eric Mazur at Harvard and had seen what he did in his course, and my course is modeled after what he did. And so for their unit in their intro physics class where they did waves, wave phenomena, longitudinal and, all the different kinds of waves.
Right.
And he had the students build musical instruments where they had to build out of garbage. They couldn't spend any money on it. Instruments that could be percussion instruments, wind instruments, or string instruments. But the boundary conditions were they had to have at least 2 octaves that they could play or more, and they had to have a tuning mechanism to be able to get it into tune, and it had to have a certain decibel level at a meter away. These were the minimum requirements, and of course if you exceed them, that's great. Does it stay in tune? That's great. But the real grading was done the way I do my mechanical properties one, where teams of faculty would walk around and have the students demonstrate their 2 octaves, show the tuning mechanism, measure the loudness, but then they would ask the students to explain the wave behavior and how the sound actually comes about. Is it a vibrating reed? Is it, what causes the air to start to oscillate? And can they explain this with the constitutive equations that they were taught to get the different frequencies, et cetera? And they asked them questions about, the envelope of sounds and why, when you play a C on a piano, it sounds different than a C on a trumpet.
Sure.
Right? That's because, so they really got into in order to do well on the assignment, the students had to actually know a lot about sound, which is what the purpose was. Now, he got the idea from this thing in Venezuela called the Il Sistema Project, where because Venezuela is such a messed up country and there's, people are very, very poor, a large number of Venezuelans said it's tragic that because of our circumstances, our students aren't learning how to play instruments in school because nobody can afford an instrument. So they started this whole project of, can we have students build instruments out of garbage? Out of
Okay.
PVC pipe they find, and then drill holes, or make a soundboard and stretch strings and use screws to tighten it up, and make things like guitars or cellos or
Right.
pianos. Can they hammer on things? And so when Eric saw that, that's where he got his idea for
I
his
see.
project. And then the project that fair he had, he called a Symposium. And I just thought
Good.
that was great. So I got to visit him and see that. And then when I came back to Ann Arbor and realized I wanted to do something in the middle of class that was like that, unlike Harvard, we don't have a dedicated machine shop for our undergrads who haven't been in their lab or design courses yet. They have a lot of resources there that even we don't have. But I thought, they can use their dorm room. And so since we were doing mechanical properties, I thought, why not have the students build a mechanical testing instrument? Certainly hardness is a pretty easy thing to do. And you could just take a ball bearing and put bricks of different weights on and measure how deep the indent is. For some students, we'll make impact testers with little sharp nails dropping down a tube. Other students made Sharpie impact or
Right.
Izod impact
Yeah.
with just a string and a rock, right?
Yep.
And it's amazing how creative our students get with these projects. But my boundary conditions were they had to be able to build this thing for less than $5. They would lose points if they spent more money. We didn't give them the money. They were allowed to use their smartphones because they already had them. If they got permission to borrow a piece of equipment, they had to talk to me first. Sure, I'd let them do that. But I didn't want them to spend any money, and they had to build it. So they had to bring their instrument to class on the day of our project fair. I didn't have a cool, slick name for it like Symposium, but that's to be decided later. And they had to bring two different samples, two different materials, or a sample and then an engineered sample, like putting notches or holes in it.
Okay.
And their job was to build this device that they could at least get repeatable results, relatively repeatable results, and show a significant difference between the two samples. And they had to bring at least 10 samples of each because they were going to have to demonstrate this as the team. You were one of our judges
Right.
one
Yep.
year.
As they're
would go
going around the room.
And just like what Eric did, the team is asking the students, why did these things happen? Tell us the mechanical properties story. What are the mechanisms that were responsible? And I'll never forget, one group wanted to measure the difference of strength between Hershey bars and Hershey bars with almonds, because they remembered the Jell-O with peanuts experiment, showing that the Jell-O with peanuts was much stronger. And their instrument was a 3-point bend test. So they had two pieces of thread attached by bricks or something across two tables, and then a third thread in the middle that was attached to a little cup that they would put pennies in to make
Right.
it heavier and heavier. And they showed they could get very reproducible by measuring exactly where they put the threads and all of that. They got very reproducible results for both the Hershey bar without almonds and the one with almonds. What was interesting was their hypothesis was wrong. It turned out the ones with almonds was actually much weaker.
Right.
And when they asked about it, they actually figured it out because they said, oh, it's probably weaker because the interface is terrible between the almonds and the peanut butter. And so we really had a lower cross-sectional area.
Right.
And it was just amazing to watch them do that. And they were very proud of their little project.
Yeah.
So
that's something they'll
always-
actually remember.
Yeah.
They had a problem, they tried to solve it, they figured it out, actually thinking about the material, which is what we
Right.
want, of course.
And so that's been a lot of fun. And again, because I have students from first year to fourth year in the class, there are a lot of students who are actually in design classes and know a lot about building stuff and designing stuff. And without even asking, I'd say about half the teams, after they demonstrated it, they said, would you like to see our MATLAB simulation? We're like, sure. And they did these whole MATLAB simulations. And I mean, I never asked for that. They just did it because that's the culture of the College of Engineering at the University of Michigan. And it's just great to see. But my favorite, I think, was the team that came up to me right before we started the class, and they said, can we go first? And I go, why do you need to go first? They said, our samples are going to melt. They were trying to measure the impact strength of different kinds of ice cream. So they had a few different pints of ice cream, and they had a string with a rock, and it goes thunk. And they wanted to measure the indent strength and measure it as a function of cream content.
Right.
So that was a lot of fun.
A good future in food science for one of those.
That's right. So anyway, we've been doing that for years, and I love it. Recently, they didn't take it as seriously as other years. I'm not sure why. I think it's because last year my class was way too big, and it just didn't work. So I'm going to be back to teaching 40 or 50 students this term, and I think it's going to be a much better experience.
Okay.
So you've done other things. You talked about your posters for that. What other kinds of projects? You're teaching Engineering 100 now for freshmen.
I sure am.
So what kind of project are you using for that?
A really big one. And I'm so relieved that today, on filming day, the students just revealed their final products and everything was fine. And I breathed a huge sigh of relief and all was well with the world. But what is the project?
Well, tell us what your Engineering 100 class even is.
Sure. The brief version is, it's a material selection and life cycle analysis course as a way to say introduction to engineering, yes, design, build, test, yes, define the problem, yes. But more importantly, as an engineer who is going to build things, hopefully, you will build things out of something. What will that something be? It better be a material. How will you choose the right one? But more importantly, how will you know what the impacts of those decisions are? Economic, right? Ethical, physical, certainly, environmental. All of these factors are things that should be considered. And so that's the theme that runs throughout the course, is as you're doing product design, as you're doing engineering work, think about all the consequences of your choices, not just the physical ones.
Okay.
That said, for the main lab project for the semester, in addition to a pretty significant environmental analysis component, students have to figure out life cycle emissions for their work and things like that. It is it's funny you bring up the MATLAB example. It is a model first, then build project. It is a metal casting project. The students are designing a product that they want to take home and use at home. So a lot of them are very practical hand tools. I have students making hammers. I have students making chef's knives. I have students making chisels. So it's very much like this can be a part of your life after this class is done.
That's cool.
And in order to go through this, the students first have to propose the project. This is what I want to make. Here's why. Here's why it's significant to me. And then they have to go through the modeling work of, here's how I'm going to cast it. Here's going to be my mold layout. This is where the metal is going to come in. Here's where air is going to vent out so I don't have, trapped gas in my product. And they have to go through this iteratively. Then they do a prototype. We just make a very simple plaster and sand mold. They 3D print their patterns in PLA. We burn them out, lost PLA. They pour the metal in, they get a prototype, and the prototype is terrible. Because it's the first one, which is the whole point of the process. The first one is almost never the final solution. And so we go back, we iterate more, and then this is the part I'm really happy worked out in the end, is we got an industry partner that 3D prints sand molds for casting. And so the students CAD up their final designs, and then we send those CAD files to the industry partner. They printed the sand molds, delivered the molds to campus, and then yesterday the students got to pour their molds that they ordered from a real, company.
Right.
So that already is a great professional experience.
Yeah.
How do you buy something that you want? That's non-trivial, really.
Right.
And we opened up the molds today, and it worked. It worked, and everything is great and wonderful with the universe. They got their knives, they got their chisels.
Do they do heat treatments or any other processing?
The material that we're using is actually one that has pretty good as-cast properties. It's a silicon bronze.
Okay.
So they could do some cold working to do additional hardening, strengthening on that. But this is a freshman course.
Right.
They haven't taken, well, literally anything. So there's not a whole lot of physical metallurgy that we get into, unfortunately. But
That's great, man.
Nevertheless, they get to make something that they can be proud of and take home with them. And they have to do all the work along the way to show, again, what are the environmental impacts? Why does my physics indicate that this should work? And then test it, and then iterate, and then, final build.
That's great. And of course, every student who takes my class has already had Engine 100 because mine's a sophomore class. It's very unusual. And even those first years that take my class are in Engineering 100. So I'm the lucky beneficiary of all the hard work you guys are doing, which is why it's been so successful for me. And it's really fun doing that.
Yeah.
Because I think it's a great idea to bring a little bit of design into all of these intro courses because, otherwise it's kind of boring to just look at FCC, BCC,
Right.
TTT diagrams. You want to know how they're used. And so it's kind of fun.
Yep.
That's great. So how do you do assessment of those projects?
For those, we are doing the very traditional formal report, formal presentation setup. And from an assessment point of view, there is a lot that I really get out of that in terms of the students' understanding of the content in the course, especially in the presentations. We're really focused on justify your decisions. Explain the process that you went through to say, why did I do it this way when I could have done it a different way?
Right.
And that really forces the students to be metacognitive and evaluate their own thinking and make judgments about their own decision making. And the ones who, it's immediately obvious, of course, when the students are presenting that I can tell who phoned it in and did that because I thought it would work. And those who say, well, here's the evidence I have to back up my belief that this was a good idea.
And so you have rubrics
yes.
to grade it on.
That's right.
Oh, that's fantastic. That's great. So I guess one kind of assessment, I probably won't do it next year, but I've done it almost every other year. As you know, when you teach a team-based class that's not required, the drop-add deadline kills you because you form good teams and then they all disappear and change.
3 weeks later.
So it's always been hard to do a team project for the first third of the class because that's about 4 weeks. When 3 weeks, people are coming and going and it's just a mess. So what I had been doing was a optional project where if they did it, they would get extra tokens for my grading scheme. But what I did for those was I had them do a project to identify an exotic or unusual phase. Remember, this is bonding, structure, diffusion, phase diagrams. And so they had to identify an unusual or exotic binary phase because the students aren't used to binary phases. And, they all say, oh, we want to do white phosphorus. I'm going, that's not a binary phase. Or they'll do gases. And I said, no, it's got to be a solid.
Sure.
Because I'm trying to, that's what's hard about teaching intro materials, because they think they know everything about phase diagrams, but of course they're thinking of what they learn in college and high school.
Right, pressure, temperature.
Yeah.
Yeah.
And then they say, oh, and the fourth phase is plasma. And it's like, oh my God.
Yeah.
So we try to change their thinking and make them recognize that, diamond and graphite are two different phases of the same element, and it's not even a binary phase. And then, of course, we try to teach them about brass and bronze and other kinds of binary phases that are, at the core of what we do in material science. And then I have them, instead of so they identify it and they have a rubric where they have to show, what's the structure of it? How would you make it using an equilibrium phase diagram? What composition would you start at? How would you cool it? And with TTT diagrams, how would you quench it carefully to get what you want for whatever the exotic property you wanted? But instead of doing PowerPoint presentations, remember, I teach classes that are 50 to 100 students. You imagine doing PowerPoint presentations with more than 12 teams? It takes at least 15 minutes for a team to do a PowerPoint presentation. And I'd be hours of listening to drivel. And then you couple in my abhorrence of PowerPoint. I hate it because things go from an Excel spreadsheet, they graph it, and they cut it from their computer, and they paste it into their PowerPoint, and it goes right from one part of their computer to another part of the computer.
Without ever going through the student's brain in
exactly.
between.
And they never think about it. And, I've always, I remember before we had graphics tools, and I had to do it back when I was a graduate student in the 70s, when I had to use my India ink and curves and my slide rule and all of that. Every data point was special. And I thought about every single data point as I put it on the page because I couldn't afford a drafts person. And they don't do that anymore, right? They just plug and chug and they get it. And I think it's important to bring something back about data and what data mean.
Yes.
And so that's one reason why I use whiteboards a lot. And so because I do that, I have the students, instead of a PowerPoint presentation, I tell them to make me a 2-minute whiteboard video that must be hand-drawn. It can either be on a whiteboard or on a piece of paper with a pencil or on a tablet with a stylus, but it cannot be machine-generated because I want them to draw it. I want them to draw all the shapes. So even a phase diagram, you have to hand-draw it. And all of a sudden, you think of the solubility curve part of the curve. Is it concave up or concave down? They have to think about that because one is right and the other is wrong. And we don't teach them the reasons for that. That'll come later when they learn about free energy curves and common tangent. And that's where the answer lies, but it makes them aware that there are these elements of the drawing that they really do need to think about. And getting everything to match up, so you have your, eutectic points or eutectoid points at the right place. It's a really good exercise for them to actually draw a phase diagram. But what's beautiful about it is they're only 2 minutes long. They get taken massive numbers of points off if it's more than 2 minutes. So they all know how to do video. They've all learned in high school, they all make videos. So they know how to speed up a video. So I tell them for equations, just speed up that part. Just don't speed up your voice to sound like Alvin the Chipmunk. So make your video 2 minutes and then do a voiceover at the very end so that it looks really nice. So the equations, when they write them, they're very fast, but that's actually a good way because nobody's, you recognize them, but you're not trying to learn the equations, and they can put little boxes around the important terms, and they can talk about their assumptions, what they knock out. So they can do this in 2 minutes very easily. And so then if I have even 24 teams, I can do all of them in 1 hour, 2 minutes per video. And the other cool thing is I get to keep them because I have their YouTube links. And I tell them, please leave them up. And so I have this nice collection of YouTube videos, which are really interesting to watch. So that's what I've been doing instead of a PowerPoint presentation. You might even consider that for Engine 100.
Well, so two things you just made me think of with this. One is on the topic of whiteboards. This isn't really a project per se, but it's something I started doing just last year, and it's been really successful, is having students give very short, impromptu whiteboard talks just on the fly in class as an assigned thing.
Yeah.
Where I might tell them a day or so ahead, hey, you're going to give a 2-minute talk on topic tomorrow, but not give them any further details than that, just enough to get their mind sort of on it so they have a general awareness and can prepare a little bit, de-stress a little bit. But then we walk into class and it's like, so tell me about topic.
Right.
And they just talk about it for a couple minutes. And it's a very real workplace dynamic. That's the intent behind that, is to say sometimes a colleague walks up to you and says, hey, what do you think about
Right.
glass transitions? And you're like, oh, well, let me think about that on the board for a minute.
Right.
And this is just how we communicate with each other. So it's a great exercise for them in this sort of unscripted, extemporaneous, but still professional communication medium.
And it goes back to some of the core things of best practices for teaching.
Mm-hmm.
When you teach somebody how to solve a problem in engineering or physics or anything, what's the first thing you want them to do?
Draw the problem.
Draw the problem. Yeah, draw a picture representing the problem so you understand what you're given. You put it into a physical context, and then you understand what you're trying to get. So I saw some students talking to you earlier today,
Yeah.
and it was clear they hadn't done that first part of just trying to understand what the current density even was. And they were trying a current density problem using the conductivity tensor operating on the, components of an electric field.
Right.
And it's not really physical when you just look at the equations, unless you're used to that kind of thing. And they should have been drawing, XYZ vector space,
Right.
and what the
Electric field this way, current that
and then
way.
so they could see what each component is, and then something schematically of what is current density. It's a flux. It's a number of electrons per unit area per unit time. And that's what was missing in what I heard. But yet that's what we all teach students about when you are posed with any kind of problem. First, make a drawing. I mean, I know the classic mistake so many students make with diffusion, in baby diffusion. You tell them, draw a concentration profile. And they wrote concentration as a function of time. And you're like, that's not a profile. It's got to be X.
Right. Where is the stuff in
Right.
the problem?
And because they just get so confused because all these different parameters are coming into it.
Right.
Because, of course, time is very important in diffusion, but it's, a different curve. At different times, you'll have different concentration profiles. And so that always stumps them. And it is amazing to me that they find that difficult. But of course, that's because I've been doing it for so many years, which is
Right.
why I have instructional aides, because they're better at teaching this than me, because I'm an idiot when it comes to teaching that
Sure.
stuff. Because to me, it's obvious. But that's
So-
why drawing on a whiteboard
Yeah.
is such a powerful thing.
With both the students teaching the students, but also, as you were saying a minute ago, being able to keep these videos that the students produce and have them for the future. A new project deliverable that I just tried for the first time this year is I did a lab project where the students were building dye-sensitized solar cells. And I gave them some instructions, and there were a lot of gaps in the instructions because I wanted students to do the research to say, what is the function of this layer in the cell? What is the material selection involved in? Why is this glass, or why is this graphite, or why is this so on? But then what the students had to deliver at the end of the project was an SOP for the project. And so next year, I'll give those SOPs written by this year's students to next year's students and say, here's your instructions for the project. Good luck.
Yeah,
If you don't like them, write better ones for next year's students.
that's great.
And I have no idea how well or poorly it will land, but we will find out.
Right. That's awesome. So you do other kinds of projects as well. So what other kinds of projects do you give the students?
One that I was forced to adopt during COVID because reasons, was doing presentations online. And there are obviously some downsides to the medium, but silver linings. Final presentations for this course that I do online, the students have to organize an online symposium. So I don't do any of the work for them, right?
Huh.
They have to choose time, date, platform, invitations, recruiting, like all of it. So it's as much a project management or an event planning project as it is anything else. So that I believe is genuinely valuable.
Right.
But another benefit of doing it online is they can bring people they know from outside the university to come see what they just did all semester.
Right.
And they invite their parents and they invite their friends. And that has been a huge positive to come out of this. You know, there will even be parents in the audience, well, the virtual audience, you know, at these presentations, and I'll even get like a DM or an email during the session, and the parents are like, I'm so glad you do this for the students. So thank you so much for this. And it's just really heartwarming to see
That's
that they
nice.
get to involve their families and say, hey, Mom, here's what I learned at school today. You know, that's something that I think has a lot of personal value to the students, and I want them to keep and maintain
Especially
those connections as
As
well.
a parent,
Right.
how many times do I ask my kids, so what are you doing in school? And I get back, Dad, why are you bothering me? And to actually be invited to see it is a wonderful thing from the parent perspective. So thank you. That's a great idea.
Yeah. I'm thinking about other projects I've seen in your classes, and one that I remember you used to do was this sort of superhero-oriented thing.
Oh, I still do it.
Yeah, so the students, as I recall, they have to design a component of like a superhero's kit or their outfit.
Yep.
And then they're doing the MSE analysis on that. So what does that look like for you now?
So again, I write a project brief where I tell them that, I give them, boundary conditions that they have to do. They can choose, some years it's been only a structural component, other years it's been electronic, magnetic, or optical. Now I let them do either.
Okay.
And, but in each case, it's like a mini design project. So they have to identify who the superhero is, and they can make up their own superhero if they want.
Great.
They have a lot of creative license. If they want to use vibranium, that's okay, but I want to see the phase diagram for vibranium. And so they usually will model that out of like iron copper or some other, and that's okay. They can attach, mythical properties to some of these things, as long as they've got a good story behind it. So they have to identify the superhero, identify the component of their superhero costume or their prop. So like Thor's hammer or Captain America's shield. There's some with Harry Potter's invisible cloak, and they talked about metamaterials and all of that. And, it's really a lot of fun. I let them plagiarize unapologetically with their images, because we don't publish these. And the images, it's much easier to get it from Marvel's website. But it makes it for a visually interesting poster. But they need to identify what they're going to make, what their thing is. Then I tell them, I want to know what are the expected modes of failure of your device, whether it's electrical or optical or mechanical, because, your superhero is going to go in battle, and you don't want stuff to break when he meets the evil villains, right? So what are your expected modes of failure, and how are you going to design against those? And they have to talk about that. And then I ask them to tell me how they're going to actually make it. How are you going to manufacture that? And how much will it cost? So it's a mini design problem that brings in things that I don't cover in my class.
again, because they've all had it in Engineering 100. And we have very diverse teams where I mix the year the students are. So almost every team has a senior who's in the middle of their capstone design. And I just want this to be fun so that they enjoy learning about these unusual materials and the properties, and then see the connection to the not quite so real world.
Yeah.
And
But
it
it's
is-
still a good chance to assess all of that sort of basic thinking like a material scientist
Right.
of what is the phase structure of this material? What is the structure property relationship that
Right.
explains its performance? So
And it's amazing, some of the things they come up with. One of these groups chose Mar-aging steel for Captain America's shield. And I was showing this to one of our alums, Ray Decker, who actually invented Mar-aging steel. And when he saw that, you could just, he's in his 90s, his eyes lit up, and he's going, oh my God, they got all the properties correct. This is great. And I've had other ones. I love it when they come up with a backstory.
right.
So there was this one poster with Aquaman, and Aquaman was coming to a conference in Novi, Michigan of superheroes. And he flew into Detroit Metro on Delta Airlines, and they lost his luggage. And inside of his luggage was his trident.
Oh no.
And he was very upset. So luckily he heard about University of Michigan had a pretty good materials program. So we went over there to get them to, build him a new trident. And it had to have, good anti-corrosion properties because he needed it to work in salt water. And he needed to make it incredibly sharp because his real goal was to impress Wonder Woman by making Superman bleed. So they have this little backstory was in there. And then they talked about how they designed it and the tests they did. And it was just fantastic. And it was great. So, they all turn in a PDF. I also use this opportunity to teach them about resolution.
Yep.
So I need to teach them, I give them templates in PowerPoint, Keynote, and Adobe Illustrator. And I always get these comments, what are these things you just gave us? They're all blank. I'm going, yep. But look at the size of the canvas. They're scaled so that you'll have the appropriate resolution, so it's going to look great on a 4x5 poster. I used to print them. Now we show them on big flat panel TV screens.
Right.
And I usually let each team, I put each poster on all the TVs around all the teams. The beauty of having a big display for every team is that you can get much higher information density than you can ever do on a screen in front of the room.
Right.
Because they're closer to it. Again, resolution.
Yep.
And so I use this as an opportunity to explain this. And of course, the best analogy is Michigan Stadium, because if you're sitting in one end zone and you look at the big display they've got, it's gorgeous. It's unbelievable. But now turn around and look at the one right behind you. And you
it's
see all these light
terrible.
bulbs. It's terrible because it's all about solid angle and what your eye is going to resolve. And so it's an important thing. And I'm not sure it's really covered many other places in the curriculum. But it's really important for material scientists because when we do microscopy, you always need a scale marker.
Right.
You should never say 2500x because then when you throw it on a projection screen, it's wrong.
Right.
So a scale marker is the way to go, and you need to always think about resolution and what happens when you blow it up or shrink it down. And these are very important concepts, so it's a fun way to get to teach that.
Yeah. Very good. We could probably talk about projects all day,
I know.
but we've probably gone long enough for one day.
I think so. So thanks for hanging out with us.
Yep.
If we get motivated, maybe we'll throw some examples of our projects up on a website so you can look in the show notes and click on it. We have to be a little careful with copyright, like I said, but this is the gray area. And we're acknowledging that, our students are cutting a few corners here or there, but these are not for publication, and they're not being used to make money in any way, shape, or form by anyone.
Just for educational purposes.
That's correct. So, all right, so see you later.
Great. See you on the next episode.
All right, bye.